So we're going to use the same kind of models that Chris was talking about before, except I'm going to replace the output. Instead of computing a single score, we're going to have multiple outputs, one for each of the tags. So for each of the part of speech tags or each of the name entity recognition tags, we're going to have a different output. And yeah, basically otherwise it's going to be very similar to what we talked about. Let's see the kind of results that we're getting and what are the crucial ingredients in these results. So the first line here shows the state of the art, which are systems by 2003 and Endo Chen 2005 respectively. The second line here shows what happens if you were just to train a good old supervised neural network separately on each of these tasks. And they don't do as well as the state of the art. The third line shows what happens if you start by training the language models that Chris was talking about, where you predict the next word given the previous words. And when you train this language model, one of the side effects is you get these word vectors, these word embeddings that tell you how to represent each word, and also give you a first layer of a neural net that takes a window of words as input. Since those models also take a window of words as input, we can use the same first hidden layer, we can use the word embedding parameters, and stick them into our supervised learning model and get these results, which are now essentially on par with the state of the art. And then you can get slightly better results by taking these naive sort of inputs. I mean, the raw inputs here are just word identities. And if you add handcrafted features like character suffixes and gazetteers, you can now go beyond the state of the art, slightly beyond the state of the art. Here's some other interesting comparative results. So we had this one before. This is a purely supervised neural network. And this is interesting. It shows how much you can gain by doing something as simple as adding a representation, distributional representation like the ground clusters as extra input features. Using the embeddings that we learned using our neural language models, we get slightly better results. And this is where we fix the embeddings, and we do the same thing as basically was done with the ground clusters. In other words, we separately learn the embeddings from the model. We consider these as fixed features, and then we plug them as inputs to the neural net. Here, what they do to get improved performance is what we call supervised refinement or supervised fine-tuning, where what has been learned in the unsupervised phase with the neural language model is used to initialize a bigger neural net and includes as its first layer these embeddings. But now when we're going to train, we're going to allow the model to change these embeddings as well. And so it's learning both the features and the classifier as well. And that gives you an extra boost. So this is an instance of multitask learning, and there are a number of cases in the literature of using deep learning for multitask learning, and Chris has already mentioned this is one of the reasons why deep learning is interesting. One thing I want to add is there's a basic reason why it makes sense to learn intermediate representations when you're going to consider multiple tasks. And the idea is that in the world around us, there are a number of explanatory factors that explain the data that we observe. And different tasks are depend on a subset of these factors. When we use multitask learning or unsupervised learning, what we're doing is we're trying to pool many of these factors and find representations that capture many of these factors. And each task is then going to be only considering a subset of them. So if there's overlap in the factors that matter for different tasks, then a shared intermediate representation like this can allow to improve the statistical power of the learning by making all of these parameters trained in a way with signals that come from the examples from all the tasks. There's another related way in which we can get improved sharing of statistical strength. Something that happens when we have multiple sources of data that are maybe very different in form. So in standard machine learning, we consider the data as one big matrix where each example is a row and each variable is a column. But in many practical settings, actually what we have as our source of data is more like a relational database where we have different sources, each involving different subsets of variables. So how can we put all of these together in one big model? In other words, to take advantage of what these different variables have in common. What we can do is essentially a form of relational learning, where each of the objects, like for example symbols like words, Wikipedia entries, that occur in the different sources are represented in the same way for all of the tasks, for all of the sources. So I'll give some examples of that later at the end of the tutorial. So these are examples of sharing statistical strength. The idea of sharing statistical strength is that we have different sources of information, different types of examples that come together to help tell us what parameter should be doing so that we have more information about that parameter and we can learn it more precisely and generalize better. So there is a particularly interesting case of this in semi-supervised learning. So what is semi-supervised learning? If you're doing purely supervised learning, you only look at the labeled examples, and let's say you only have green and the blue example, you would probably choose a linear classifier like this. But if I give you these unlabeled black examples, you would probably choose a classifier like this, which is very different. So what it means is we're taking advantage of a particular structure that exists in P of X, the input distribution, to tell us about how we should do P of C with X, or particular supervised tasks. And in deep learning, what we're doing is we're assuming that there are explanatory factors, or features, that are good at explaining the variations in P of X. For example, here the features might be projecting along these directions, tells us a lot of information. I mean, the two directions of interest here are these direction and this direction. And these two directions would come out from sort of trying to explain P of X. It turns out that one of these two directions is really useful to explain P of C given X. All right, so now let me say a few words about one of the unsupervised learning tools that is pretty common in the deep learning literature. So we've already seen the idea of predicting the next word as one of the unsupervised learning strategy with contrasted unsupervised word learning. We've heard about RVMs, restricted voice machines, which we're not going to cover in the tutorial, but we're going to talk here about autoencoders, which are actually very close to RVMs, and there's interesting connections between the two, but they're kind of simpler to understand. So, in particular, they have been used for fixed size input representations like diagonal orders. So let's go through a little bit of PowerPoint this graph. So what is an autoencoder? It's very simple. It's just a multi-layered neural network whose target output is equal to its input. Well, you're going to say, well, why would that be useful? You already know the input. Why do you want to predict it? Well, the thing is, we want the output to be similar to the input on the training examples. And because the network is regularized one way or another, it's not going to be able to make the output close to the input everywhere. Instead, it's gonna learn to have small reconstruction error in order to get the prediction to be close to the input, only on the training examples and in other places where it generalizes. So in a sense, it's modeling about the input distribution. It's making the reconstruction errors small in places where the inputs should be plausible. And you can have something as simple as the usual sigmoid or hyperbolic tangent with some parameters, fine transformation of the input, and then this part, we give it a special name. We decompose the NLP in two parts. So we have the usual outputs, which we call reconstruction. We decompose into an encoder part and a decoder part. And in this example, the encoder is one layer and the decoder is one layer, but you could have deeper autoencoders. And in this example, we're using squared error as the loss, reconstruction loss, but you could use other things like KL divergence for discrete data. It makes more sense. So now, to understand autoencoders, let's look at something simpler, which are essentially linear autoencoders, and that's PCA, principal components analysis. So what is PCA doing? PCA is going to give us a new representation of our data by projecting inputs x linearly, multiplying by a matrix that goes to a lower dimensional representation. So we have a rectangular matrix here, and this matrix is going to be chosen to contain in its rows the principal eigenvectors of the covariance matrix of the input distribution. And then once we projected, so that's going to be our encoder, is going to be just Wx. And the decoder is just going to be W transpose times the output of the encoder. So they're both linear and transpose of each other. So that's the reconstruction function. Now geometrically, what is going on? We're taking our data, the red points, and we're looking at the leading directions of variation. So the principal eigenvector of the covariance matrix would be this direction. And we're projecting on the manifold corresponding to the variations in those directions. So the encoder here, the encoder output here would be a coordinate along that manifold, and the reconstruction would be the actual point into the input space that is on the manifold itself, corresponding to that projection. So this idea of manifold has been very popular in machine learning in the last decade. And what it says is that for many of the problems of interest in machine learning and in AI, the data concentrate in some in the small regions in space, in lower dimensional manifolds. So regions where the density is high and which occupy a very small volume. So in continuous spaces, you can think of these manifolds as sheets that can have arbitrary shapes. You can see an example here with faces, which undergo things like rotations or changes in expression. So if you move in data space, you make small changes and stay on some kind of surface. And if you think about objects like images of digits, you can move, stay in the regions of high density images, images that are plausible by doing things like rotating and scaling and so on. In the case of discrete spaces like in language, one way to think about it, we can't really think about continuous manifolds. What we can think of is having regions of high density where small changes are only allowed in certain directions, and such that those regions of high density occupy a much smaller volume than the ambient space. So if I take a random sequence of words, I get garbage. So the chances of producing, so in other words, like English sentences occupy a very, very small subset of possible configurations. As soon as you have something like that, then all of these manifold techniques can potentially be useful. So what is going on with autoencoders? How do they help us to capture manifolds? So we've already seen that the linear autoencoder, which is the same as PCA, captures linear manifolds. What nonlinear autoencoders do is they can capture nonlinear manifolds, like this one. And why do they capture nonlinear manifolds? Well, let's say we have a training example here, and we want to minimize reconstruction error. And for this to happen, we need to find an encoder, in other words, a representation for this that will make the representation for that one different from the representation of its neighbor. So in other words, the variations around that point in the direction of the manifold we need to preserve in the representation space. On the other hand, variations in directions orthogonal to manifold we can throw away, and because the training is regularized, as I said, if it wants to throw away all the directions it can, it's only going to keep the directions in the direction of the manifold. And because of the nonlinearity, you're going to get the possibility of actually capturing a nonlinear manifold rather than a linear one. So the important ingredient here is that we need somehow to prevent the autoencoder to learn the identity everywhere, because that would be trivial and useless. And there are various ways that have been proposed to do that. One, sort of the old way is like PCA, what we call endocomplete, where there's a bottleneck. In other words, the representation of the code is smaller dimensional than the input. But the modern ways of doing it are different. They allow representations that can be larger, and in fact, because of that, they can represent arbitrarily complicated distributions. And so one of the early methods is the idea of adding sparsity in the representation. So making the hidden units, the intermediate representations, zero, often zero, or near zero. Another approach is the denoising approach, so it's called the denoising autoencoder. And the idea is going to train the autoencoder slightly differently, so that it's going to map noisy input, corrupted input, back to their clean versions. And the contracted autoencoder is very similar to the denoising autoencoder, except it does it in an analytic way, so you add a regularization penalty that makes the encoder have small derivatives. But all of these have the same effect, that the representation that you're learning is unable to make reconstruction errors small everywhere, so it wants to throw away the information, as much information that it can, but at the same time it needs to reconstruct, and that forces it to learn the structure of the input distribution. And we actually have now recent math to show that properly, that you can learn to estimate the input distribution using these kinds of things. So for sparsity, yes?
How are you autoencoder to capture the pan of the cooker? So we have the input output and have it autoencoder.
Absolutely, yes.
So how do you understand it? So to connect to the manifold theory, the cooker and minimizing the construction error. What's the connection?
Well, you can look at what hidden units do and interpret them as by looking at the words that they like, that makes them active. So words that can be, for example, easily substituted for one another will typically end up having positive connections to the same hidden units. And some of these analyses have been done.
So there are 3 different variants of autoencoder.
Yes.
Some of them especially advantage for this case.
So I can only respond sort of from an empirical point of view. So what we found is that for, at least for the experiments we've run, the denoising autoencoders with sparsity penalty, which combines these two things together, seems to work really well. And so if you look at the papers last year from my group on applications of denoising autoencoders to, for example, sentiment analysis and things like that, that's what they use. And we also use this to win a transfer learning competition that took place last year, which had 2 data sets that were language data sets. Okay, so let's try to understand better this sparsity thing. And this is an example from vision, which is sometimes easier to visualize, as you can imagine, where the model is trained on image patches. And so these are the kind of examples it sees. Actually, it sees little patches. And what you see here are the features learned by the first layer units. So each little square here represents the weights, or the, if you want, input configuration to which the unit responds the most. And all of these are different units. So you can think of them also as bases to explain the kinds of data it sees in the training set. So if you have an example, like a test example, it turns out that you can explain it, you can generate it by combining the features, a small number of these bases. So that's where sparsity comes in. Instead of explaining your input with many hidden units, only 3 of them here are enough. And just a linear combination of these 3 units is going to reconstruct this thing properly. So that's the idea sparsity, that if you want to represent that input in the space of what is learned, you can have a representation that has mostly zeros, except in a few places, which are the few units that, together with some coefficients that are here, explain your example. Reconstruct your example properly. One nice thing about autoencoders is that nonlinear autoencoders is that you can stack them to obtain deeper autoencoders or to obtain deep neural nets that you can then use to for doing supervised learning tasks. So let me actually go in detail of how this is done. So let's say you start with some inputs. You're going to train an autoencoder. It's going to give you some features in the encoder. So this is the encoder. Here's a decoder for it. I'm going to train the output here to try to reconstruct the input. Once I finish training by backprop and gradient descent, I can throw away the decoder, just keep the encoder, and use that new representation of the data to train a second autoencoder that just sees the data in that form. And once I've trained the second autoencoder on top of the first one, I can throw away the decoder for that one, just keep these two levels.